Hi, Charles.
Listen, they are homework quizzing next door for the first 20 minutes, so I'm going to try to talk softly so as not to interrupt their quizzing time. All right? Huh?
Is that why Miss Foden was here?
No, Mrs. Foden was here to bring in our successor. So are there any questions about any of the stuff that we did in class on yesterday? About the gamma function, the beta function, and its used to determine integrals. So remember, we had the integral from 0 to 1, t to the alpha minus 1, 1 minus t to the beta minus 1, dt. And we said that we could evaluate that in terms of the beta function. Gamma alpha, gamma beta, over gamma alpha plus beta. Any questions at all about that manipulation? Yes, sir.
Well, this is more about the
Sure.
those manipulations. But the other day you went over the integral from 0 to infinity of x, following that and e to the negative 2x. And you said in class and to the notes that would be like the coefficient of epsilon.
That's right.
In the expansion.
That's right.
But can you explain how you just get that? How you know it's the coefficient?
Sure. Let's go through this again.
Well, it's a little different from when it's just negative.
No, it's not. It seems different, but it's not. Let me go through it, okay? So, the integral we're asking about here is the integral from 0 to infinity like that. So what we did was we consider instead, right? Yes. And what integral are we considering? That's right. So whenever we have this logarithm, we consider instead x, the thing that we're taking the logarithm of, to the epsilon power. All right? So I would say right? And then what did we do? Do you guys remember what we did? All right, okay. This, I think, is the point of confusion. In order to determine the value of this integral, we are going to do a u sub. We are, and then we'll express it in terms of the gamma function. That is absolutely true. That part of the process is different for e to the minus 2x than it is for e to the minus x. That is 100% true. However, this part of the process, where we determine where the integral appears in the Maclaurin series expansion of the result, is exactly the same. Okay, so it's like we have two sides of the equation. One proceeds exactly the same way, whether it's e to the minus 2x or e to the minus x. The other one proceeds in a slightly different way with this additional u sub that we did. All right? So let's do the side that tells us what coefficient it is. So I'm going to say x e to the epsilon log x e to the minus 2x dx. What do we do with the e to the epsilon log x? Does anybody remember? That's right, we're going to throw the Maclaurin series expansion. All right, now I've done that a couple of times now, so I'm going to do it faster this time. Okay? So we would say right? Does that make sense to everybody? So it is at this point that we recognize that the integral that we are interested in obtaining the value of manifests itself as the coefficient of epsilon to the first power. because it's log to the first, right? And it even is nice enough to come with a 1/1 factorial, so we don't have to bother with an additional manipulation at the end. What if we wanted log squared? Then it would be the coefficient of epsilon squared, and I would need to multiply by the 2, because the integral associated with log squared appears with a 2 factorial. Does that make sense? Which at least is nice enough to just be 2. All right, and is not like 5 factorial, which is 120. All right? So, does that answer that part of the question? Why is it the coefficient of epsilon?
Yeah, I think I was more asking about.
Let's do the other side of the equation. All right. So on the other side of the equation, we have this integral here. I don't have enough space to do it right here. So I'm going to move over to the middle of the board. All right? And I'll say, look. I need to do a U substitution. The reason I have to do a U substitution is because this integral does not directly take the form of the gamma function integral representation. Right? Forgot. So it's integral from 0 to infinity, x to the z minus 1, e to the minus x. It's not appropriate to have a 2 there. Happily, that 2 is something we can easily remove via scaling substitution. So I'll write u equals 2x, which means x is equal to u divided by 2, right? Now, one very easy way to do this substitution is just to go through and recognize everywhere you see an x, you get a 1/2. All right? So I'll get 1/2, 1 plus epsilon. Dx also gets a 1/2 because it counts. You could think of 2 as representing a scale, like meters, right? So if x was measured in meters, then a change in x would also be measured in meters. Does that make sense? So it also gets the scale. Sometimes that's what people forget, which is why I point that out. And then I'll just have, right? And this will allow me to immediately complete the integral. Right? Remember, you have to add 1. Okay? You can blame Legendre for that. All right? All right, any questions about that? How would we proceed? Yes, sir.
Well, the coefficient in that expansion of epsilon, you need to expand that, so you take 1 plus epsilon times gamma of 1 plus epsilon, and then you use the expansion of ln of 1 plus epsilon, or you take e to the power of it, and then you take the expansion of e to the power of it. And then
That's exactly correct. So Mr. Stone points out that we would say 1/4, right? And then we would have e to the minus epsilon log 2. And then he says we're going to use the recursion relation. 1 plus epsilon, gamma 1 plus epsilon. That will give me gamma 2 plus epsilon. So I'll say 1 plus epsilon, gamma 1 plus epsilon. All right? And then Jack's argument is that the reason that we are interested in gamma 1 plus epsilon is because that's what we have a Maclaurin series for. Does that make sense? That's what we have a Maclaurin series for. So that's how we're going to be able to pull the coefficient of epsilon to the first. So I'll say 1/4, 1 plus epsilon, and then I've got this big exponential, which I'll now write out. It will look very, very, very scary until we recognize that we only want the coefficient of epsilon, at which point it will simply give it to us. All right? xp minus epsilon log 2 minus gamma epsilon plus the sum from k equals 2 to infinity minus 1 to the k zeta k by k epsilon to the k. Does that make sense to everybody? All right, now what would you say as far as our integral is concerned? What would you say about the behavior of these contributions? They can't contribute. Why not? That's right, because they only contribute at order epsilon squared and higher. And I'm not interested in that, so. Does that make sense? So therefore, the value of this integral will be 1/4 1 minus log 2 minus Euler gamma. Okay? 1 minus the natural log of 2 minus the Euler-Mascheroni constant, all divided by 4. Okay. Any questions about that? Remember, this process is very important. We're going to be doing it repeatedly. So if there's something about it that you don't understand, it's best if you ask it now. All right? It's okay if you ask it later, and some of you will. That'll be fine. No problem.
So like we just, like we know, or we can take, we know what power of epsilon we're trying to find from what's a natural log.
That's right, from the power of the law.
And then because those two integrals are equal, we just find what it is on the side of the equal side.
Exactly. Exactly. Okay? Does that make sense?
Yeah, I was just confused from the part where it's 1 over 2 to the 2 plus epsilon, because when it was just negative, it's multiplied back by the fact.
It's fine. It's always confusing. This process always takes people some time to get. Okay? But I found that it's best to handle organically. All right? I go through the process once. I point out all the things that I think are going to be stumbling blocks for most people, and then I just allow everybody to bring up their own stumbling blocks. All right? And that happens slightly differently from year to year. All right. Yes, ma'am.
So how did you get the 1 minus L and 2 minus
All right, so let's go ahead and do our expansion. Remember that this is e to the box. So therefore it will be 1 plus box squared over 2 factorial plus box cubed over 3 factorial plus so on and so forth. But what would you say about box squared? What does it start with? That's right, it starts with epsilon squared. And that means that it can't possibly contribute to the integral that I'm interested in computing the value of. Does that make sense? Is everybody okay with that? This process in particular bothers students a lot when they're first learning. So I really want to make sure that I cover all of the questions that you guys have. But I'll continue to do so over the next couple of weeks, okay, as they come out. Anybody else about previous material, and then we're going to move on. Anybody? Yes, sir.
I have a question concerning this process of the data structure.
Okay.
Yeah, and it is on this yesterday, computing was the data function or square root.
Yes, I did.
What would you consider this? You never really equivalent
I didn't show it explicitly, but I was equating it to an expansion. I'll tell you what, I plan to do a different one like that, all right, right now. And so hopefully that will be good enough, and I won't redo the one from yesterday, okay? All right, everybody okay? All right, let's move on. So suppose that I was interested in determining the value of this integral. What would I consider instead? That's, all right, so I would, so I'm considering, what was it? The integral from 0 to 1. 1 minus t, I'm gonna write it in calculus simplified form. And then what? T to the epsilon, that's correct, right? dt, of course. All right, so I want to consider that. Oh, okay, great. So now let's go ahead and write the part that Anshu was asking about, all right? And then we'll try to determine which coefficient, all right? So we would say, integral 0 to 1, we would say e to the epsilon log t, we would say 1 minus t to the 1/2 dt. Is everybody with me on that? Now, I've done this expansion a number of times, so I'm going to again do it quickly. All right, so this will be the sum from k equals 0 to infinity, right? I'll have epsilon to the k by k factorial, 0 to 1 log to the k of t, 1 minus t square root dt. All right, just like that. So, you see how this one, this integral is the coefficient of epsilon to the k in this expansion, right? So where would we find our integral? That's right, it would be the coefficient of epsilon to the first. Does it make sense?
Yes.
You're all good then?
Yes.
Good. All right, so let's proceed with our effort to determine this coefficient. So what would you say about the value of this integral as it relates to the beta function? So what would this integral be? Gamma. You always add 1. Okay, that's the part that people miss. You add 1, so it's gamma 3/2. Gamma what? 1 plus epsilon. Over gamma what? 5/2 plus epsilon. Because you always add in the denominator. All right? So now what would we do if we're interested in an expansion? Whatever will we do? No. What do we do first?
Use recursion relation.
That's right. Recursion relation to bump him on down. All right? This is where something a little bit different is going to happen. Clearly, this is 1/2 the square root of pi. Right? Everybody's good with that part. Then we'll have gamma 1 plus epsilon. That one I don't need to bump. Does everybody agree with that?
Yep.
Divided by, how will I bump this one? 3/2 plus epsilon, gamma 3/2 plus epsilon. Then what? 1/2 plus epsilon, gamma 1/2. All right, what's the issue? Oh, shoot. It doesn't cancel. Oh, I must not have bumped it enough times. What do you guys think? Will it ever cancel? No. That's very unfortunate. So now let's talk briefly, all right, about a process that you might consider doing. And let's talk about whether or not it's true. Okay? So I'm going to do this in pink. So, I want an expansion. We all good with this, right?
Yeah.
We all good. We all good. We all good. That's the one that we're having trouble with, right? So let's see what we can do with that expansion. So I'll say 1/2 plus epsilon. I have an expansion for gamma 1 plus epsilon. So you guys tell me something. I'm going to go ahead and just write out, and I want you to tell me whether or not what I'm writing is correct.
Oh boy.
All right, shh. Not saying you're wrong. All right, here we go. This equals sign. Yes or no? Is it correct?
Yes.
Yes. Yes, it is. That's correct. How about this equal sign? Yes or no? Is it correct?
Yes.
Yes, that's correct. When what? When 1/2 or -1/2 plus epsilon is less than 1. Now, it's valid whenever it's less than 1. It's useful whenever it's much less than 1. That's true. But, all right, what did we want? We wanted the coefficient of epsilon. I want you to think very carefully about this. Which terms in this series will contribute to the coefficient of epsilon? All of them. And that is the problem. Okay? It's not wrong. It's just not useful. It is right. It's just not useful. Okay? It's not useful. It doesn't give me what I want. Okay? We got to get what we want. So what we need to do, yes, sir.
Could we use an expansion like this to like find out like the sum of all of delta over 2 to like delta k?
Zeta.
Sorry.
That's okay.
Zeta of k over 2 to the k and the sum of all of those.
You could do that. So what Aditya is asking is, could we do the integral in the way that we're obviously going to do the integral in just a few minutes, and then use the result in conjunction with this series to determine the value of an infinite series involving zetas? And the answer is yes. We can do that. We're not going to, but we could. All right? Absolutely. However, does everybody agree that this is not appropriate? It's not going to give us the order of epsilons. We need something else. All right? And this is going to be a major result. It is called Legendre's duplication identity. All right? Excellent name. Legendre duplication identity. All right? And we're going to go ahead and derive it right now. All right? This is going to take some space.
Sideboard.
We did, but there's somebody else. She's right around the.
Oh, okay.
He was going to come and observe her after she was done her homework things, but I don't.
It's totally up to you. I'll come see you. Okay, fine. I was just gonna watch the derivation. To see if I understood any of it, you know.
So, I want to remember this. I want to remember this because we're going to be coming back to this. All right? So I'm going to go ahead and simplify it a little bit. All right? And then we'll erase it and get the Legendre duplication again. All right? So I'm going to write this as 2/3 square root of pi. Okay? And then gamma 1 plus epsilon over 1 plus 2/3 epsilon. And then 1 plus 2 epsilon. Gamma 1/2 plus epsilon. All right? What did I do? I was rewriting it, so I had to do some steps. That's right. I factored it out because it's not useful to do an expansion that starts with a number that's not 1. I'd rather it be 1. All right? So what I did was I factored out a 3/2 and a 1/2 out of the two denominators. 1/2 divided by 1/2 is 1, so that part cancels. Right? And then, of course, I took the reciprocal. All right. So, Legendre duplication. This is not the only way to derive this identity. I just think it's the cleanest way. Okay? going to begin with the integral from 0 to 1 of t to the z minus 1, 1 minus t to the z minus 1 dt. Now you guys tell me, what will that equal in terms of the beta function or in terms of the gamma function? That's right. Gamma squared z over gamma 2z. Now what Legendre was interested in, this was the 1800s because that's when Legendre was alive, all right? What he was interested in was studying the behavior of 2 times k factorial, given the behavior of k factorial. So if I knew about what 100 factorial behaved like, he wanted to study the behavior of 200 factorial. All right, so he was trying to get at that. This gamma 2z represents this 2z factorial, right? A little bit, there's a shift, right? Whatever, okay? So what Legendre was going to do, and I don't think that this is the way he derived it, all right? But what we can do is we can consider a change of variables in this integral, turn it into another beta function integral, and then do it a different way. So here's what we're going to do. We're going to consider this u substitution. U equals 2t minus 1. All right? Now, I don't expect you at this moment to see the utility of that substitution. Let's just take it for granted right now. And then as we move through, we'll see why this choice of u is so lucrative. Okay? So, of course, the way that we do our u substitutions in this class is we're going to solve for t, right? So I'll say t equals u plus 1 over 2, right? All right. So this integral, if I employ this u substitution, will look like this. All right, there's a couple of pieces that students often miss when they're doing this substitution. The first piece, and also the most universally missed, is changing the integral bounds. And that's because people always forget to do that in BC. All right? If you don't change the bounds in this, it doesn't matter what else you do, you're going to get it wrong. Okay? So, when t equals 0, what is u? Negative 1. When t equals 1, what is u? 1. You can think of that as part of the motivation for this choice of u. It gives us a nice symmetric integral, all right? And it's also going to be beautiful what happens inside, all right? So what about t? T was u plus 1 over 2. So I was, oh, this will be 1 plus u over 2 to the z minus 1. And then what's 1 minus t? That's right, it's 1 minus u over 2. What is dt? What is dt? du over 2. All right. So, let's be appropriate. All right.
Yeah, it's supposed to be clean.
That was good. All right. So,
Nice window.
all right. So I'm going to take out all the 2's. What will happen? I'll have 2 in the denominator to the z minus 1, 2 to the z minus 1 again, and then another 2. So what will I end up with in the denominator? All right, 2z minus 1. Everybody with me on that? Okay? And guys, what do you notice? These are to the same power. So what might I do had I taken algebra 1? That's right, difference of 2 squares. Everybody remember difference of 2 squares? All right, so, yeah, you better. All right, so it'll be 1 minus u squared to the power of z minus 1 du. Now, what do you notice about the integrand? especially those of you with 0 or not 0 credentials. What do you notice about the integral? It is symmetric, it's an even function of u. So what will I do if I'm integrating from -1 to 1? That's right, I'll do twice the integral from 0 to 1. Everybody with me on that? Twice 1/2 2z minus 1, 0 to 1, 1 minus u squared to the z minus 1 du. Is everybody with me on that? Now, I'm going to ask you guys to have a little bit of clairvoyance and tell me, what will we do now? What will we do? Hint, we did things just like it yesterday. You sub, that's right, we're going to sub again. We're going to do v sub. What will v equal? What will v equal? Just u squared. Just u squared. Okay? Because then it'll be 1 minus v, and I'll get a power of v, and I'll have beta function back. Right? Heck yeah! Alright.
Clean Dr.
Hey, look, I know I'm being videotaped. So, v equals u squared. So u equals v to the 1/2. du will equal 1/2 v to the minus 1/2. dv, won't it? So I'll say 2, 1/2 to the 2z minus 1, right? Now how about here? When u equals 0, what's v? 0. When u equals 1, what's v? 1. So the limits don't change here, which I think is part of the reason why sometimes people come from PC with this feeling that the limits don't ever change. Because sometimes they don't. Okay? Anyway, all right, so we've got that, and then we need 1 minus v to the z minus 1, and then 1/2 v to the minus 1/2 dv. Is everybody with me on that? Heck yeah. So now what? What happened to the 2? The 2 will cancel away. He all gone. All right? And so what we'll end up with is, can everybody do this integral now easy?
Yes.
What is it? Let's read it off. What does this integral become? Just the integral. Gamma z gamma 1/2 divided by gamma z plus 1/2. Hey guys, guess what we needed?
Oh my God.
We needed gamma something plus a... Amazing! Almost as if it had been engineered that way. I mean, so what we would have here is 1/2 to the 2z minus 1, and then gamma z, gamma of 1/2. What's gamma of 1/2? Root pi, that's right. Over gamma of z plus a half. And this is the Legendre duplication identity. All right, now, we're not going to do it in this form. I think that the form that Legendre used it in was where he manipulated it and said gamma 2z equals. Okay? That's the form that you usually see it in if you look it up in standard reference texts. All right? It says gamma 2z equals blah, 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 blah. We are not going to care about that form. We're going to use a different form. What do you suppose we want?
Gamma 1 over.
Gamma z plus a half, right? So what we're going to say is, let's manipulate it to give us gamma z plus a half. Alright? So I would say gamma z plus a half is equal to, all right, what we got up in here? It looks like 1/2 to the 2z minus 1a, right? One of the gamma z's is going to cancel. It'll give me square root of pi gamma 2z over gamma z. Is everybody with me on that? Does that make sense? We're just moving it around, all right? Just like algebra 1, all right? I mean, the symbols are different, but, all right.
Question.
A
do
equals
it
something.
entirely.
Anyway, all right, so any questions about that? I have a question for you. Is this the form that we're going to want if we're going to want to do expansions in Z? No. What would we prefer to have instead? 1 plus. How could we give ourselves a 1 plus? We'll use the recursion relation, right? We got to bump these guys up 1. I believe we can accomplish that. So what I would need to do is multiply the numerator by 2z and the denominator by z, right? But that would modify the expression. So what we're going to do is we're going to multiply by 2z over 2z. Is everybody with me on that?
Yes.
Good on that.
Oh, that's so clean. Yeah.
Oh, it's absolutely gorgeous. Hold on just a second. All right.
I think we need to
So now, all right, that 2z is going to bump that one up, right? I only need the z to bump that one up. So that means I got me an extra 2. What do you suppose I might do with that extra 2? That's right, and it would be so much easier to remember. All right, so I'll have 2 to the minus 2z root pi gamma 1 plus 2z gamma 1 plus z. Okay? And this is the Legendre duplication identity in the form that we're going to use it. Now, I want to take a couple of minutes to talk about how I think Legendre developed it, because he didn't develop it like this, I don't think. He might have, but for whole numbers, he was looking at it in a slightly different way. I'm going to do this on the sideboard, so Aditya, if you want to turn the camera, if somebody wants to do it. Yes, sir?
Sorry, I have one really quick question.
Yep.
What happened to the square with the, so you have gamma 2?
I had gamma squared here, and I had a gamma here.
Oh.
So one of them has vacated the premises. All right, so,
Oh, was there an extra 1/2?
so guys, let's do this with gamma of 3 plus a half. I'm going to take z equals 3. All right? So Legendre has told us that this will be 2 to the minus 6, right? Because z equals 3. 2 to the minus 6 root pi. And then the 1 plus, what does that make it? If it's gamma of 1 plus something, what will that make it if it's a nice whole number? The factorial. Right? Remember gamma of 1 plus, remember Legendre's shift? Right? So this is going to be the factorial. So it'd be 2z factorial, oh that's 6 factorial. Divided by z factorial, well that'll be 3 factorial. Does that make sense to everybody? Okay? Now, this is going to be root pi 2 to the 6 downstairs. 6, 5, 4, 3, 2, 1. 3, 2, 1. Now, as long as we cancel this in the proper way, we can see very clearly why it is that Legendre's duplication identity works in the way that it does. However, I stand by the fact that I think it's cleanest to derive this way, because the counting is sort of awkward when we do it the other way. All right? But we have to cancel properly. If I cancel this 3, 2, 1 with that 3, 2, 1, it won't be clear. So here's what I'm gonna do. I'm gonna cancel that 3 with the 6. I'm gonna cancel that 2 with the 4. And I'm gonna cancel that 1 with the 2, just so we can see it properly. So I have 3, all right. I have 3 2s. 2, 2, 2. Hey guys, I have 6 2s downstairs. That's more than enough 2s. So I'm gonna go ahead and cancel those 2s out. All right. What am I left with?
Square root of 5, 5 halves, 3 halves, 1 half.
That's right, square root of pi. I'm gonna leave it as over 2 to the 3rd for the moment, Amit, but I agree with your sentiment. Right? But look, guys, this is 5 halves, 3 halves, 1 half, root pi. You see that? So we get all the odd numbers, right? And they have their associated factors of 2 downstairs, right? And we get so it's the recursion relation all over again. Does everybody see that? All right? Does everybody see how that works? I'm pretty sure that that's the way that Legendre originally got it. Okay? And there is, by the way, another multiplication identity that is valid for other fractions. So it would, for example, give you gamma of 1/3 times gamma of 2/3. Okay? Or like you can go all the way up. There's like a triple identity. I think it goes like this. It's like gamma of n plus 1/3 times gamma of n plus 2/3 times gamma of n times some weird factors is associated with gamma 3n. And that more general one is called Gauss's multiplication formula. And he does it for any multiple for gamma. But it's only really useful for Legendre, for the duplication. Because in the duplication, we have a value for gamma of 1/2. It's equal to the square root of pi. Yes, sir?
So to drive the other one, could we do z minus 1 and kz minus 1?
I don't think that the other ones are as clean to develop in terms of the integral representation for the beta function. Because there's more. You're not going to get 3 gammas out of
You
it.
have to do like generalize the beta function by multiplying more units.
You might do that, which there is a generalization.
Right.
Or you might generalize this concept. Okay, and then look and be like, oh, I'm gonna have, these ones that have remainder 2 when divided by 3, remainder 1 when divided by 3, and multiples of 3. Okay, and then you would just do that analysis. You can look that up if you want to. We're not using it in this class. Okay? All right. So, any questions about any of that business? This is our identity that we're going to want to use in the form that we're going to want to use it. Okay? Right here. So now what I need to do is work with my pink expression. So I'll have gamma. And gamma of 1/2 plus epsilon, so that's going to be 2 to the minus 2 epsilon, right? Root pi like that. All right?
It sounds like you're saying root pi.
Root.
Yes.
Oh, that didn't mean anything years ago. All right, so. All right. People started saying that about 3 years ago. Anyway, all right. So.
What?
So guys. Shh. So. The square root of pi, there we go, cancels away, right? And I would write this as 2/3. Hey, what coefficient are we looking for?
Epsilon.
Epsilon to the first, right?
Oh, that's actually better.
Geometric, right? So I'll geometric. Geometric. Two to the positive 2 epsilon, which I'm going to write like this. And then here we go, gamma squared. Bless you. Bless you. Okay. Pretty sure that's what we have. Now, here's something wonderful that happens. Remember how awkward it has been that our gamma function Taylor series has really been a Taylor series for the natural log of gamma. So that means that in order to get gamma, we have to exponentiate that series. And exponentiating a series is a little bit awkward. So, how easy is it in general to square a Taylor series?
Not too bad. For small values, push you
What about dividing two Taylor series?
That's the worst.
If a Taylor series already exists in the exponent, how easy will it be to square that? You multiply it by 2. E to the z all squared is e to the 2z. Does that make sense? How easy will it be to divide?
Not so bad.
What will you do if you take e to one power series divided by e to another power series? You'll subtract. Boy, I can do that. So what I'll say is, hey, let's just combine all this business together. All right, this is going to look very complicated the first time we see it. All right, but it's not going to be that bad. It's all going to be okay. Here we go. Right? And then I'm subtracting this series. So it's going to be plus gamma 2 epsilon minus the sum from k equals 2 to infinity like that.
Square.
Are there any questions about that? Any questions about that? Oh my gosh, it looks so complicated.
Wait, is that you cancel that?
Question for you. Yes, sir.
Wait, so did you move the gamma function into the exponent or use the?
I used the Taylor series. Remember we said gamma 1 plus epsilon is equal to e to the minus gamma epsilon plus log, or plus sum from k equals 2 to infinity, negative 1 to the k, zeta k by k, epsilon k.
Makes sense, okay.
Okay? So if I've got gamma squared of 1 plus epsilon, then it'll be e to the 2 times all that stuff. If I'm dividing by gamma, then it'll be subtract all that stuff. So this part here is gamma squared 1 plus epsilon. This part here is 1 over gamma 1 plus 2 epsilon. Does that make sense? All right. What happens to the Euler-Mascheroni constant? Cancels out. That almost always happens when you have a beta function. The beta function almost always sees the Euler-Mascheroni constant vacate the premises. All right? So if you're doing one of these calculations and you don't see Euler-Masch exit stage right, then you should take another look at your computation. Okay? So now the pink exponential will be 1 plus stuff in braces plus 1 over 2 factorial stuff in braces squared plus 1 over 3 factorial stuff in braces cubed plus on and on and on. But what coefficient were we interested in? Epsilon to the 1. So what will happen to those other powers? They don't contribute to our value, right? So therefore, the integral that we are interested in has value let's see what we got up in here. 2/3 here we go. Minus 2/3 minus 2 plus 2 log 2.
Oh, just flies.
And that's the value of that integral. 4/3 times log 2 minus 4/3.